Hello, hello everyone. Welcome everyone to join this session called Yu-feng Ho from OpenGeoHub. And today it's more like an introduction section, so I think most of the room have like introduction lecture, and I wanted to also have some more introductions since last time I was presenting the them and throughout this time I developed a little bit of the functionality around this kind of factor data. If you're not familiar with factor data, it will be fine. We'll go through some basic introduction and slowly get into this kind of data and also do some hands-on practice about this topic. So the topic here, apparently from the screen, is the introduction of the cloud-native factor format. So anyone heard about cloud-native before? Yeah, okay, half of them, yes. So we will go through the factor, and then we will actually talk a little bit about what is cloud and what is actually doing with our research and our operation system. So yeah, let me show you everything. Oh. So let's get started. So I will have some kind of like a lecture, but also hands-on. So I will spend around 45 minutes approximately to talk a little bit about the basic knowledge, and then another 45 minutes we'll do some hands-on practice. And because this is 1.5 hour lecture, so just feel free to be more relaxed and slowly learning. And if you have any questions, you can just interrupt. We have enough time. I hope so. So just interrupt me at any time that you like. And the first we are gonna introduce a little bit raster and vector, and then we'll talk about what is analyzed ready data that has been used for Earth observation research or environment research that could require this signal data that should be understandable and interruptible to be used. And then we were talking about how can we access all this analyzed ready data and using this cloud-native format to access. And so we were talking a little bit about the raster. So just like also a rough introduction, and also the main point is the native format, native vector format. And then we'll go to the case study about accessing this kind of space-borne LiDAR data set, which is above 1 petabyte in total. So how can we efficiently access all this data? And then later on we will go through the hands-on to actually play with this factor data. And first of all, my boss required me to say that this is the project that we support by developing inside our open project. So we do this project, we do a lot of open source developing and also open data, open sourcing the particle. So this is one of the results that we also present in the process to how to organize these big factor data to let user to search, easy searchable and interruptible. So let's go to the basic about raster and factor right now. So I think I forgot to ask, man, how many people understand raster and factor in this room? Okay, yeah, most of the people. So I can probably like just give it fast. So raster, it's more like in a grill cell, and the factor is more like you have a factor of the information that you put in the format like points, lines, polygons, and you can see this data format in the real world. So this is like a Python environment. You can see the raster data is actually gridded. So you have this kind of like 2D matrix or even like 3D matrix of the 4Ds with a different array format. And the factor is more like a table. So you have one geometry columns and another are the attributes associated with that geometric point. So in the real case practice, we can have like cellular imagery storing the raster. So we have like represented image, and Also, digital allocation model, you estimate and then you interpolate into the grid cell. So, and the factor data set we probably mostly use in Earth observation is to store the institute data or the per copy that we are also covering about the LiDAR data, and also sometimes serve as a base net so that you can query and render from the spatial database that also we were storing into this format. This step further to actually get into Earth observation, we have to understand the scale of Earth observation data. So this slide is about few years. So it shows that really the scale of getting more like high resolution or more detailed Earth observation data will cost us. So you can see that if the MODIS is considered like 1 time, the Landsat is 64 times bigger than that. And the Sentinel is 625 times bigger. And the Planiscope in 5 meters is 6,000 more than MODIS data. And then you try to store the data. For example, like Planiscope for the whole world, you can probably easily end up with petabyte of data. So to actually let people interact with those data, we need something that's more easily to be assessing different skills or like different applications. So also the factor data has been stored into the real world. I also excel a lot as before. So you probably will work on some geo-package data and also like shapefile data. They might have 20, 30 megabytes. But now we talk about like gigabyte of the data in one geo package, even like petabyte of data in one single data file. And this is also the problem that we're trying to address when we come to like potentially increase the data size and how can we easily access all these data sets, even like it's more than your computer capacity to reach them. Yeah, so this is the example that the LiDAR point data set storing this 3D information. And this is just a show off like the data point around Europe. So you can see how dense though this point is, and each point have like store over 100 attributes. So it's really hard to just reading into your workstation and really be easy to find the useful information for you. And this is come from one of the research published by Wageningen in 2021. So they talk about like the big data Earth challenge. So the top 5 challenges are more like, how can I really find this data and how to access and how to interoperating all this data? Because if you are really first getting into this field, you found out there are so many remote sensing data, and then you have problems to actually filter out that's not used for data, and we try to treat the data as in your area or interest or the related information. So they have this kind of limited processing capacity. The growing data volume is the second one, and data is not standardized, and too many like platform or proto that serve this data, so you don't know where to find it. So this is the nowadays the big data challenge brings us. And let's talk a little bit about this analyze 3D data. By the way, do you have like a timer so I can see that how much time I have? Yes, thank you. So let's talk a little bit about the analyze 3D data after we have this big data scenario. So you have a lot of different data, but you don't know that this data is actually work for you. So you have to do a lot of research to understand how to produce the data and how to process the data, and also how this data represented to you. And somehow data is not correct for your format, and then you have to do some quick processing until you reading for your specific application. So reading the data specification and documentation and kind of like compare and improve the data has been a lot of work for the Earth observation scientists that are doing this kind of thing. But so at this point, we are thinking about, well, how can we just make environmental scientists, so like the actual scientists or policymaker, use this data more efficiently? Just we can get rid of all this stuff that we do by ourselves to actually improve the data, and we just provide the data that is already kind of high quality that you can just analyze or make policy upon of that. So that is the whole idea of analyze ready data. So we get the raw data, and the EO scientists, they find a way to actually improve the data quality. And if you can't analyze ready data, even like you do another machine learning model or feature engineering to get like an extra layer, or you can just directly use for comparing statistics to trend analysis and to inform decision making. So this what the point that we come up with this idea to have analyze ready data. And this is not like very new ideas. Even like NASA have been kind of promote this for a long time. So this is some keywords from so we can kind of like reduce the time users spend on for processing the data, and also make it more accessible by telling a real registry, and also remove do atmospherical corrections for the Landsat data. So that's how has been applied for such a long time. And this is one of the examples that we will see. It's like if you wanted to estimate the spectral reflections on the ground, you cannot just take the raw satellite imagery, because you have the atmospheric interruption in between the surface, the real surface, and the satellites. So so this is the example. If you try to derive an DVF on the bottom of atmosphere and top of the atmosphere, you have some correlation, but they also have some bias to actually estimate the surface reflection. So people tend to actually get the real, more accurate bottom of atmosphere to run the analysis if you really wanted to analyze it at the ground. And let's come to also a part of the cloud optimized data format. So we talk about the analyze ready data and how can we access the data for the user, and we need that to be more accessible for the user. And this is one of the talk from 2021. So I think 4 or 5 years ago. 4 years ago in summer school, that people present the idea of the cloud optimized GOT. It's for raster data. So it's like a tile GOT data has a specific order of data and metadata, so you can search a specific tile and do the HTTP request. So it's HTTP request is like a unique object on the internet, and if you request for that object, then it will only return all these objects from a big cloud system. So it turns to be more. Okay, I will show later on the kind of like the structure of this cloud. This might it will be easy to visualize in this way. So we have this here original data, and then we do compression, and then So we have 3 things for cloud optimized GOT. First is have to have a compression algorithm to actually reduce the data size. So it will be easy to host and transport the data from the internet. To imagine if you have like a 100 gigabyte of data to be transported, it's faster to transport 50 gigabyte of data instead of 100. So this is how the compression works if you're trying to move the data around. So in cloud optimized GOT, they have the definition of doing the lossless compression, and also create this telling overview that you can. So they create the overview that aggregate the pixel into different overview, and when you try to search in a different scale of the range, you will get a different overview. And when you look at the overview, you have more interpretable of the data. But if you go inside to be more detailed of the teeth, that you can see more detailed information of the lower, like a higher level of the tile, and you can retrieve the data is actually from the lower aggregated pixel, and until the end of it will be like the real data, we have like a maximum level. But I'm not really talking too much for the rest of data here. I think there will be more lecture from my colleagues in the next few days. Interesting. I think it's like David will also cover a little bit, and Leandro also cover a little bit of this topic. So I just kind of just give it a taste of how this cloud optimized is, and use the GeoTech example. And then you have the HTTP request. So you send a request to different data layers and only retrieve a small subset of this layer. And then you don't have to, for example, you have this big amount of data, but you can only retrieve a small set using HTTP request. So that is the delicacy of cloud optimized data. And there's a concept also cloud object storage. So actually, you can see here, if you look at your file, you will kind of find out, for example, I can show a little bit. If you go to the file, you have all these connection links. Okay, I go to home and I can go to OGHTML25, I go to the file, and all this file is like interconnected. But in the object-based storage, the files, they are actually just representing a unique ID. And when you request it to get an ID, you don't actually go to the search system to actually find a connection with each file. But they have like a metadata to be able to search that. But you want to request a file, you only need just to go directly to the data location of the disk and retrieve that directly from there instead of going through all the filtering in advance and to actually reach the data as you're doing your local file system. And also, the cloud optimized data format enables the lazy loading things. So lazy loading is a term. Has anyone heard about lazy loading? Right? Okay. Yes, quite a lot. So lazy loading is a term when the client tries to get the information from the remote places. For example, I wanted to access the cloud optimized data from the cloud. And the first thing the lazy loading do is to retrieve the metadata. So you go to the clients interact with the cloud optimized format with the metadata. So the metadata, for example, in the geospatial world, you have the spatial instance, you have temporal instance, you have data variables, you have chunk size, etc. And using this metadata, I can do filtering. Before you actually read the data, I can filter out, okay, I want the spatial instance for only Wageningen. So the data that not in the spatial instance of Wageningen will not be selected. And also I can select the time periods or for example, I want the data only in 2025. So I can get this data only in 2025 and then those will not be selected. And later on, the cloud will interact with you to retrieve the data in parallel because the data in the cloud device is the same as like we see before as a tile or as a chunk. So they only retrieve the data that you're asking for instead of getting all the data to your local computer and then you try to filter the data in fast. So in this way, you only get a data chunk which is relatively smaller than the whole cloud device data. So in this way, you can really reduce the data transportation throughout the internet and also be more efficient to retrieve the data that is actually needed for you. So this is the idea of the lazy loading. And okay, just some slides about also the cloud optimized data has been used also in AWS, Google Cloud, anything like that. And at the end, we come to this analyze ready cloud optimized concept to actually combine these two things. So we want the EO scientists to provide the data that is analyze ready, but not only the analyze ready, but also cloud optimized to that another user that search for this data set to be more accessible. So analyze ready data is the term that we use to describe the data set that it's really easy to interact with. And also it's high quality for real-time analysis. So it stands for complete, consistent, and the current up-to-date and the correct data. So this is like the current status that we wanted to operate the data as the EO scientist to provide for the user. So yeah, it's probably one of the main project output that we are considering OpenGeoHub to actually have this idea of this one and then provide all these sample and data sets that can be used. So yeah, the last bit, Google Map also a classic like cloud service that you can, when you zoom in, you get more information because you retrieve this information after you query specific regions. And also when you get deeper, you actually query more detailed information at the spatial instance that provide you this data. And let's come to the main point. Okay. So I'm here today. I wanted to get more example of the cloud native format. And so we were talking about the raster. Now we have this same concept of the cloud optimized in the factor data. So in the factor data world, that we can easily compare the old time cloud optimized formats on the left side. Yes, also on the left side. So on the right side, it's the kind of like current state of art cloud optimized format. And the OpenGeoHub is one of the early ages cloud optimized factor data that embed their spatial index inside it, and you can query this visual index directly from the client side. And they have more. They have a pro is they have a complete features, and they have no size limit, and they are like they already outperform some data IO for shapefile, GeoPackage, and GeoJSON. And you're also very compatible with, for example, CronGIS or ArcGIS, I believe. And compared with the other side, the new format we call it GeoParquet. So it's the parquet. So when you see on the ground, it's the parquet. It's the same thing. So they kind of like arrange the data into a chunk of the chunk. So that's why I think that's why they call it parquet. So they have chunk of the data. And the Pro is really, they have a column indexing and the column metadata that you can select the data individually. So you don't have to read all the column. You can select the column that it's in your interest. And also it's highly compressed. So I have done some tests. This is actually maybe 10 times more compressed than the GeoPackage. It's GeoPackage is also similar size with the OpenGeoHub. So when you think about like having 10 gigabyte of the GeoPackage, if in GeoPackage is probably 1 gigabyte or 2 gigabyte. But you have some also comes. It's not really good integration into GIS software, and also there's no embedding special indexings in this data format. And also there's a discussion already. People like wanted to have the spatial index in the GeoParquet, and developers say no, we implement the spatial index is become too slow, so we actually like do opposite than what we wanted to achieve. So with that, kind of implement a spatial index. So thank you. So that was the end of the discussion. You can still find it online, and people talk about, let's implement this online. But yeah, I don't see that coming, and also probably we don't need that. Yeah, and this is an example of the cloud optimized. So when you move the your bounding blocks, so you actually retrieve only the data that your bounding blocks intersect with. So that is the beauty of the cloud optimized format. Okay, so so going into a little bit detail of the factor data, we have to first understand the basic concept of the spatial index. So why we can arrange the data in a way that we can efficiently access that we implement some algorithm to optimize the search. So we have R3, quarter tree, and KD trees, which is in a way we have the indexings that record what kind of hierarchy level of the data should be. So if you imagine this is the world, so you want to actually find something here, and then you can get the level of start from R2, and then the R2 go inside all the information in R2, and then you read R6, and then you got R16, and you get the actual area you want to go. It is more efficient because you actually don't read the big chunk. You don't read R1. You don't read the place R1 over here, but you only read R2 because you have only intersect with the big bounding box with R2. So this is the classic information of the R3. R3 is stand for a rectangle tree. So it's the way that they kind of organize this data in kind of like a chunk of the chunk, and then go to hierarchy to find the specific data. So just like as here. So when you do the query, the spatial index will let you go select one R2 and R1 or R2. And when you get to R2, you get to another level, and then you only have to choose the data. Half of the data you already abandoned because you don't really need for a specific region, but half of the data related, it will start going to deeper and deeper level and try to find the most matches location for your data set. So in FloodGeoHub, that we did a lot of research also inside it, and then they have implemented this hyper R3 index. So that's why we mentioned this spatial index, because when you really read this data, you will find out that they are actually implement this index in the format when you read it is OpenGeoHub or other software. So so in the specification of FloodGeoHub, they have a specific header that organize this data in the R3 index. So the R3 hyper index. So hyper index is the way that optimize the search distance. So it's a bit deep, but yeah, you don't have to really know the detail, but it's just the optimized ways to actually find the closest distance. Am I correct? The closest distance for different spatial location. And this is the way that it optimizes the data. So you have like this U, and then you kind of bend into this shape. And this shape, the distance, when they come closer, they are easily to connect it. And geometrically, they has been improving a lot in performance. Yeah. So just to say, but this is kind of like old style, and the new style here we are introducing is the GeoParquet. So GeoParquet is a data format that has there's column coordinated, and it have row group and column chunk inside the data. So actually they chunk the data in the way of selecting the columns and the rows based on what you want to query on the fly. So the Parquet is organized from the partition to the file level, and the file level has some row group. And in each row group you have a column chunk. So you can either filter according to the partition to find a specific Parquet file in your data set. And then you read a file, and then you read the file, you'll get to this footer metadata. And this footer metadata just what we have said, it's the information of the spatial instance, temporal instance, or this kind of column information. And I go to the row group. So row group is the data stored in chunk in the order of the row. So for example, you have the data of the time, for example. So you collect the data every year from 2024 January to 2024 December. So the column chunk organizes all the rows that are in the same month will be stored closely. So you have the column row index with, okay, this is January data, this is February data, this is March data. So when you do searching, when you read a file, you can filter out, okay, I want to have the row group only for January. And it only will retrieve this row group to your column side. As we say in the web optimized concept, we have this lazy loading, only load the row group that in the month we are interested in. And inside the row group, we have the column chunk. So the column chunk is the so if you imagine the row group is horizontal, and the column is the vertical chunk for that. So the column is okay. I have 10 different attributes. So I only want 2 attributes. I can just take these 2 attributes as a chunk. So I don't need another 8 attributes. So that's the kind of like a metaphor of having this row group and chunk. So you can filter out either by row and filter out even by column. That is the beauty of this data format. And this one is PM type. So this is kind of like a new things that is the best for the geo visualization. So if you're interested in the web service, this is one of the good. So it's a single file format decipher a single file and then tile the packet data according to their according to like a geolocation. And this is the one of the, we call it serverless data, because if you serve this without having a server, it's very handy because you don't actually stream all the data to the front. So you serve small chunk to each user. And this is also very out of state cloud native vector format. And I can show you a little bit of what we have done with this data format. So I hope, so this is one of the platforms we developed in the OpenGeoHub. So it's called Echo Data Cube. So it's basically the data cube for like Europe. And then we use this PM tile to cloud optimize the data. So if you go here, you can find, you can also play on your laptop. It's just called Eco Data Cube. If you search Eco Data, you will find this app. So if you go here, you can search fail boundary. So this fail boundary is the data produced by a planet, and they make automation of file boundary delineation to actually capture all the file, all the boundary of the plot. And then if you zoom in, you can see that all this kind of red point, there will be more and more pop up after you zoom into a layer. And this is the kind of the size volume that we're looking for to have. You see all the file, and when you reload, and you can load all this kind of field boundary in the front end immediately. That is the beauty of also cloud optimized data format. And in specific case, it's a PM tile. And yeah, and I also highly recommend to watch this video from Brendan Liu. I think he's also Taiwanese, and we met last time in OpenGeoHub, and he introduced me this data format. Yeah. So it was actually funny. He was Taiwanese, but he didn't live in Taiwan. So he lived in California for his whole life. So I tried to speak him in Mandarin, but he cannot understand, and then we switch back to English as the conversation proceeds. But he actually had a lot of talk about this kind of PM tile data. He's the main developer, and he's a big maintenance of this. And if you're interested, you can watch the video to actually understand what is PM tile. So I will put it here, but you can access the slide from GitHub or like Mattermost, so you don't miss out too much. And yeah, and then at the end, I wanted to actually just summarize a little bit of the common vector format that we have introduced. So no matter how good the cloud optimized is, we have shapefile, GeoPackage, GeoJSON, and PM tile and Flux GeoGov, and GeoParquet, and the last is PostGIS and PostgreSQL. So I would introduce things. So people think about, like, if you have the cloud optimized GeoT, like why you wanted to use different kind of format. Why did different formats still exist? But I want to explain a little bit why it's still very important. Because when you think about like doing easy stuff, you don't want it to go for too complicated solution because it's not necessary. So if you just wanted to, look at your data a little bit, let people downloading from your messaging channel, I think the best way is the shapefile, GeoPackage, and GeoJSON, because everyone can open that in QGIS, in ArcGIS, because it's the format that everyone uses that for such a long time. That all the software have a good compatibility to all this, like we call it grandpa, or I don't know. The grandpa format. Okay, I call it this way. And so this is a good way that also I like to use this for like specific checking to actually visualizing in QGIS and overlay with other layer on the GIS software. So this is just so essential for most of the use cases. So you don't have to really like abandon completely. No one will trash it by using shapefile or not using GeoPackage. And the second, like PM tile, we will say that it's really good for cloud optimized data visualization purpose, because I tested also a little bit for that to actually do data operation. It's just not that easy as you're doing a GeoPackage or GeoParquet. Okay.
Yes, PM tile is also quantized. So it doesn't store the actual coordinates, but it's the coordinate quantized to a grid. So that's why it's also not nice for analysis.
Yeah, exactly. Yeah. So so they say like the tile of the data. So for visualization purpose, they will query all this polygon, and also they have some compressions. Also, will reduce a little bit of the reduce a little bit of the precision, because you actually don't need that when you do the visualization. You cannot distinguish a line with 1 centimeter and 5 centimeter on the 30-meter scale of data resolution. So they also do that to actually improve the data visualization in this way. And later on, we have OpenGeoHub. It's very cloud native format. It's one of like maybe it's the most mediocre one between like local GeoJSON stuff and GeoPackage. And it's also set a way that we can store things in cloud native format in one single file. But also I also test a little bit of performance. It's just not as fast as what we're going to talk about, the GeoParquet. So GeoParquet, I think, is one of the best that we found right now for fast data transportation. So because they compress the size, plus they have this kind of feature for optimizing for assets in column. So it's for now, it's one of the faster and more compressed data format that's suitable for big data query and storage. So if you wanted to consider like storing big amount of data and you are training the machine learning model, you are also doing a lot of I/O for your projects. This is one of the way that you would like to go. And the last is PostGIS and PostgreSQL. So this is more like a server-side solution for the vector data. And I like this format because it has features for running servers. So you can keep this running in the background, and you can keep updating this data appending to this database. You don't have to rewrite the whole data file, because in most of the file between they are more static files. So when you write the data, it's the physical object over there. It's not the database. So the database have the features to actually, when you have new data, when you want to delete the old data, you can drop off, or you can append in the data in real time, because you actually don't touch another place of the data. But if you do like this kind of data format like GeoParquet, because you have to write the full metadata, so you have to open the data anyway to actually re-index everything. So this is not like a very good way if you want to keep appending or keep updating your data protocol. And you will probably like to go to PostGIS and PostgreSQL to work on that. So for the former like EMTile and the GeoParquet as a cloud native format, it's more suitable for archive data. So you already finished a big project and you want to show people that what is the result of this project, and you put one Parquet file online and people just accessing, and you don't actually update it in 6 months. So that will be perfect for the use cases. Okay. Any questions right now? Any? Maybe I'm talking too fast, or is everyone like catching up? Yeah.
So what is actually?
Can you turn it up? Turn it up. See that?
Thanks a lot for those. Okay. But what is actually the advantage over having an API that also lets me only retrieve the data that I want to have?
Okay, that's a very good question. So the advantage is so imagine that you have to I don't know what will be the best metaphor for that, but I will just try to explain the future world. So the advantage is it's when you have like data from server side and you want to do operation in your locals, and so you have a laptop, but your data is Google Drive, for example. And Google Drive is not cloud optimized, but they store like an object on the cloud. And you're trying to operate with this data, you have to download the whole data from Google Drive to actually make it to a local file and do the operation in the local to actually get filter out this data to, for example, you download the file is 1 gigabyte and you only need 10 megabyte of the information in this file. You still need to download 1 gigabyte of the file. And this increase the data accessing time, but also they create a kind of like a data storage issue because you actually duplicate the data running on the cloud and running local with most of the information that is useless. And to go into like operational size, if you wanted to do bigger stuff, it's not like just 1 gigabyte or like 20 megabyte. It's maybe like 1 petabyte to 2 gigabytes. So in this case, you already have to pay so much for data transportation. If you wanted to put the things on the cloud, and you have to transport 1 petabyte of data from one of the cloud storage, they probably will already charge you money because you are streaming too much, you are occupied too much on the internet. So this way of optimizing on the cloud is helping you to save money off your budget also, because you only need to stream 2 gigabyte of data instead of 1 petabyte in the real-time situation. So you can save all this computational power and more efficiency on data accessing and storage. So I hope that it's easy to understand. If you don't understand, you can talk to me after the lecture. I will probably give you some real-time examples, so it's better. Yes.
Yeah, thanks for your presentations. So in case of cloud metric is QT, cloud optimized QT, we have a kind of cataloging system in Stack. Is there any kind of similar cataloging system in cloud native vectors?
Yeah, it's a very good question. Actually, I wanted to show. So that is one of the Stack catalog I'm trying to show you at the real case problem. So we will show you later, but we basically tile this geoparquet into it's kind of spatial temporal organized or spatial temporal order in order to be easy access. So it's also like kind of like slowly adapted for us. Like we used to work most of in raster data, but now through OpenGeoHub, we also create some stack for specific like vector data, and we are debating still developing this kind of like stack standard for this. But this is one of the examples I'm going to show in the later on class study, case study, and also I believe it's a good way to actually access the big amount of the vector data using the concept of stack. Yes. Well, I already get caught for some of the material I'm gonna teach, but okay. So, have any questions, or I just keep continuing? I have 30 minutes. No, 45 minutes left. Yes. Yeah. So, if there is not any too much questions, so we're gonna dive into some real-time, real case study that you can actually like use your hand to work on them a little bit. So we're doing this. The topic is about big data from space. So we have this spaceborne LiDAR. This is one of the spaceborne LiDAR is global ecological system dynamics investigations called JEDI. Everyone heard of JEDI? Yes. So this is kind of like a huge NASA project that store a lot of LiDAR data in the NASA server. And the problem that we found for this data is because it's operational system for according to the orbit, so that the satellites will fly from here to here. For sure, they don't go up and out at the end of the world because the Earth is not flat. So it will come back again and come back to the other side, and it just keep running in the orbit. But for the convenience, they store the data in the way of the orbit. But this is actually not too optimized for if you're interested in specific area, because the next orbit already goes down, or the last orbit will go up. So you actually don't retrieve too much data from this specific area. And that is a problem because you have to actually find out all of the data that have been come across for the area that you are interested in, and also filter out most of the data that is useless because it's not covering or this is purely noise. So that's why we trying to, I will see this problem with the data structure and then the file in the JEDI data set. And we try to use conquer by the Parquet. So, so we're using Parquet to reconstruct the global LiDAR data set. So the first thing we have to do is to define the spatial temporal tile for the Parquet instance. So when we read the data, we actually write into spatial temporal blocks. So for example, this orbit is running like this, and everything passed through this will be right into this chunk. So you have JEDI orbit from JEDI orbit 1 and JEDI orbit 2. When they were the point inside this chunk, they will be right into the same partitions that we were saying the spatial temporal block that we also later on arrange as a step. So in this way, we are able to stream out all of the JEDI data into one static geospatial spatial temporal block. So this is kind of like visualization of how this orbit works, and how this kind of spatial temporal can capture the data that inside the instance based on the Parquet functionality. And then we create this stack that would be used for our tutorial, like the hands-on. So this we name it as OpenGeoHub JEDI level 2, because we reconstruct the nodes, so we figure out some lower level points in order to keep the data set more analyzed ready. So user can just use it and do a range of the purpose without like getting into so much trouble with accessing the data and also interpret this data set. And yet now we can start from hands-on. So allow me to show you. So I think when you get the Mattermost, can you everyone go into Mattermost? I will post things over there. So here. So we create this OGH stuff. Let me see. Summer school. Here is my. Can everyone, do everyone have the Mattermost? So if you go to the town square, I post this GitHub repository there, so you can go there and ask it. I may talk too long for that. It was easy. Okay. I wait for a bit. Okay. I hope everyone got to this stage. It's everything okay? Well, I gotta take a move to get to this stage. Yes. Let me see how many people watched. 0. Okay.
It's a different thing.
Okay. Even sure. And okay, and then you go down to this README, and this is a slide that you can access where I presented, and you can go here with the Colab hands-on, and click the link. And this link will lead you guys to the Colab environment. The thing is that in OpenGeoHub we start using CodeLab because we don't have to compile most of the library from different OS systems. That's from more handy for us to start a lecture. So that's like we like it. Just, does anyone have any problem? Can you access? No? What does it say?
Signed out.
You have to sign out. You have to have a Google account. No one. If you don't have a Google account, just look at the lecture and then you can access the code later. So just follow me if you don't have a Google account, okay? And if you have a Google account, you are free just to enter the this code app.
I want your authentication.
Yeah, me
Yeah. Good.
I think you do need to make a copy.
You have to make a copy, yeah, because I don't allow people to play around. You have to save a copy in your drive. It's here. Go to file and then save a copy in drive and create your own copy. Otherwise, we all work on the same environment. You probably will. It'll be a lot of fun. Yeah. Did anyone get into it? Okay. So, so I will show you a little bit how to play with this OpenLAN map Jedi data. So in very fast speed. So if you go here, I think you can also go this one. This,
You know how to copy of it?
So, also, you can access the stack over here. I also posted in Mattermost.
Is it? Yeah.
They can help. If you're ready, probably help someone see if they're having any problem.
I also had
Okay, cool. Come here, the file. I think you can say the copy in Drive.
I think the problem is most people don't end up in
Yes.
So I think that's authentication issue blocking people away.
Ah, you mean this one?
Yeah.
Let me see.
So
Anyone with a link? Let me post again.
I just removed the
maybe you set them to.
four letters of the link.
Yeah.
Added for
Let me try here. Just can you try to see if we can also find that's one here?
so what I'm doing is I just need to move to the last part.
Yeah.
Just question mark. So then you access.
Okay.
Yeah.
Okay. So after the question mark,
But then how do you say?
like this. Yeah. Sometimes the authentication can be mess.
Okay, now it's.
Yeah. Just as you say, try to remove the question mark after the question mark, and if you still have a problem, just let me know. Okay. And when you get here, go to File and save the copy in Drive, so you actually end up into your own copy. And they will create a copy one for in the browser, I assume. And then you can just work on this one and close your old one. So go here, file, save the copy in Drive. Yeah, you will have copy one. Everything all right? Then we can slowly show the next step. So the next step is very important. So we're gonna go into the data set, as I also posted in Animals. So we go here, there's a link, and you click on this link, you will go to our OpenGeoHub stack browser. Yes. Yeah. And in this stack catalog, we document a little bit of this data set, but we also actually writing some more specific specification to work with that. But it's still also some kind of a basic information for this. So they have a description and all of the keyword of what is this actually data set working for. So data is estimate the 3D structure of the planet Earth. So they kind of like what is that? Emit the waveform from the space, and as the LiDAR waveform records the vast stagger LiDAR energy, they actually calculate the distance between the satellites to the ground. So you can use that to map the canopy height and also to map the ground, because you will have most of the return that hit the ground and return to the space station, and some of the return will hit, for example, trees or buildings and return to the space station. So that is how the way that this data has been used to map, for example, tree height or like terrain or like elevation height on the planet surface. And this is the data set that we reconstructed from the orbit oriented to a geoparquet data format. So if you go here, this is icon. So you can see that the icon will start from longitude, latitude, year, and you can find the specific year and latitude area to your places. So for example, I go inside here. So each region have visualization how this kind of data has been organized. So they have this orbit in 2026 that passed through all this area. So it should be maybe revisited 2 times, because one time is over a lot of time probably. One time is over here. So you can have all these kind of like laser wave of like a track. And if you go here, you can actually copy this URL. And if you go to the browser, you can see that they actually end up to be a Parquet file at specific longitude, latitude, and at a specific year. And you can also download it. Oh, I don't want to download it. Yes. So you can find it using this stack browser. But so you can go to see all these data sources that they have a visualization of where it is located and which year the information. But this is all not the best way that I like to use this data. I really like this one. So actually, I organized all these data sets in a format of the GeoJSON. So you can see here in the collection level, when you go to access GeoJSON stack items and you open that, there's a GeoJSON that you can show on the map. So this map shows all of the tiles that I have for all the information for each tile. So for example, this tile have the ID of longitude 20, latitude 5, year 2023, and the size in megabytes, and how many points this tile have, and the years and starting date and end date, for example. And so we're gonna like work with this directly. So if you come here and use the copy URL, and go back to your script. From here you pass. So when you look into this OpenLemma Jedi level 2 and go down, you can see that want to read some using GeoPandas to read file, and then you can find this link to the stack items GeoJSON. And if you don't really find it, I also can post it here. So just copy the URL on the MetaMost. But if you see carefully, you can just go to stack and ask like a collection level and go to access GeoJSON and copy the URL. From here, you can access. Okay. All right. I will probably keep going, so we can keep it on that. So, anyway. It's also not mine. So I can start. You can just pass through this HTTP, and you can already reading these items. So the items have this information. For example, size in megabytes is for like each tile, how many megabytes in this tile, and how many points in each tile, and what is the year, and what is the start and end. And also geometry. Using that, we can visualize it and try to filter out by geometry. So I have the form to actually also visualize it. You can just run the code like accordingly. So the code theoretically are more executable. So you can look at this, also can run by yourself. So I can run these items, the data items that I just saved here, from the stack items to show up all this visualization of the whole world. So you can see that each tile have how many points, how many data in megabytes for each tile. And then we can also do a summary of how many megabytes of data this is. So I divide by 1,000 for all of the items, capture out the size in megabytes, and then divide by 1,000. So I transform in megabytes into gigabytes. So this data set in total is about 700 gigabytes. If you wanted to download the whole thing, so for sure you don't want to download the whole thing because probably nowadays you have more storage on your laptop, more than a terabyte, but you still don't want to 700 gigabytes of data in your local. So you probably just wanted to save on the random cloud that we have, so you can just access from here. So the total size of this data set is about 700 gigabytes to run this code. And yeah, this is show you how many gigabytes. And in this tutorial, I wanted to actually just go somewhere smaller. So we get this data from the Dutch border, so the Dutch province border. So the Netherlands is kind of like smaller places. So we would like to just work on the data that related to the Netherlands. And this is the data set we can download by the GADM. And you can, after that, you can open that in the GeoPandas. And you can also visualize this as the tile with of this kind of data set with your tile. So actually overlap with all these two tiles only out of the thousands of tiles you have seen, like Netherlands only overlay with these two tiles. So I only need to access these two tiles instead of all of the tiles. So that is the beauty of this organizing. So after I also access this tile, I can do some getting some bounding bugs that intersect with the icons to get the Jedi data that's pulled into the Netherlands province border. So using this one, I'm able to get bounding bugs. And then this one is, so I'm gonna open that. It's like all the tiles that overlay with the Netherlands. So as you see, it's two like special tiles, but also have years. So 2021, 2019, 20, 21, etc. So we have a few tiles in the spatial domain. So how many we have? We have 10. So in total 10. And then we see this. First, I wanted to download it. So it's easy to first we do like reading the cloud optimized formats in the local, and then we accelerate to cloud. So I download it directly into my Google Colab, and then I can just read this data from the GeoParquet. So I can just read from GeoPandas. So I can just read this file locally through Google Colab. So Colab local, it's local on the cloud of the local of the system. So it's more like a virtual local, but it's still local for Google Colab. Yes, it's a bit complicated, but yeah, you can see that here you read 2.3 seconds for 13 millions of row. If you run, if you read the data from a Parquet, it's also 95 columns. So you can imagine like how big is the actual size that you have been reading. So this is the example, like the case of how Parquet can compress the data into some very accessible way that you can read like a million of the data in just seconds. And also there are some packages that that help us to filter out the row group. So actually say that we have this row group and columns chunk. And but this is not like the functionality is not appear in GeoPandas. So we try to have used in other ways. So here we use a package called PyArrow. So it's the package that specific word for the Parquet arrow, which is where the GeoParquet has been developed accordingly. So using this library, you are able to run something we call it predicate. So predicate is just the concept of the lazy loading. So you do the filtering on the cloud to retrieve the partial data using this predicate. So this is the concept that has been commonly described. So it's called predicate pushdown. So using this concept that you can access the metadata of the Parquet and do some filter before reading all this data. So in this way, I filter out with the quality flag. If the quality flag is a good quality, I retrieve this. If not, I don't. So when I run this, I get 1.4 seconds just to read a million of points. It's less than what we retrieve, 1.3 millions, and the same number of columns. But if you implement this pushdown, you can reduce the amount of data you retrieve to your local because you already filter out when the data is in the cloud. And this is the concept that we were just we will keep describing in the lecture. You have to filter out the data before reading to save the cost of reading a big number of data, and also reduce the data transportation. So that is what we talk about. And later on, we can also use this package to run the okay, this is too much. Okay, to run the column. So this is actually a column selection. Sorry. So I can just select a few columns to reading. So what will be happen is that you can read only 0.03 seconds for also 1.3 millions of data, but only 3 columns left because I'm only interested with these 3 columns. So I don't need other 92 columns. I can just reading according to my column I specify for this. So it's really extremely efficient when you have like a big table, like you only need some of them. So this is the way to reading. And if I combine both of them, it's the example 4. So I can just read. Okay, it's not getting faster, but it's getting less data. So somehow you also get not that fast if you do too much filtering because it's actually already too fast. So it doesn't save too much. So also for optimization mindset, you probably go, I don't actually need to do that. But in the good mindset also, if you read less data, you actually create less data storage problem in your local or your memory. So it's always good if you lost some if you lost some processing time, but you create a data storage efficiency. So this is the case that you can see that they are really quite similar to the time of the reading, but you can read less data. Yeah, this is from the package of the PyArrow. Has anyone gone through here, or you have stopped for some places? And yeah, it's the first time you heard about this package, or you haven't used it also before? Okay, yeah, so some people are the first time. Yeah, and later on we can run another library. So again, we went to this GeoPandas, now PyArrow. And the last one I really like is called DuckDB. So it's DuckDB. So I will search a little bit also this one. DuckDB. So it's one of like a data managing tool that's open source developed. And this specific use for like spatial data querying and stuff. And he already built based on the SQL language, but it also have the API for the Python and R and Java, so and JavaScript. So this is one of the tools that enable us to do more spatial filtering, because PyArrow is, although it's officially supported by the Parquet developer, but Parquet, they used to work not for the geospatial data. So they don't actually deal with too much geospatial data, so that you see that when you filter out the data, it's only for, filter out the quality, filter out the color information, but actually not working in the geometry. So DuckDB enable us to actually work directly with the geometry to retrieve the data that is specific in your geometry before actually reading it, which is such a beautiful thing. So here, the DuckDB has been designed to work with a well-known text format for the geometry. If you don't know, you can search on the Wikipedia. So this is how we get transformed into. This is the union of. So I forgot to show. So this is what we wanted to retrieve: the shape of our geometry, the whole Netherlands. We wanted to get the data point for our Netherlands. So to intersect with the Netherlands, and then retrieve points only for the Netherlands for the whole for each file. So for DuckDB, you can run this API just by import DuckDB, and using this from Jedi, from the local file, I can actually just retrieve it, and yeah, and you spend like 2 seconds also, 1.3 million cell point, just reading by this API query. So this is a SQL query if you know SQL, but if you are a Python user, you just use Python. So you just like pretend to know SQL until you actually think, oh, SQL is actually a good thing. So it's the same thing. And also I can use this spatial kind of like what is like add-on to play with the intersect. So you can actually filter out the target using this intersect. So they take the geometry from text, for the well-known text that we have for the Netherlands boundary, and to overlay all the points geometry from the Jedi. So this is the format where my Netherlands boundary, where's my points, Jedi points in the Netherlands, I will retrieve it. Otherwise, I don't retrieve. So this is kind of like what they say. So you can read that. Yeah, it's taking a bit long, but you can actually filter out most of the data, because if you wanted to filter out data, also fine, but you will also take this amount of time just to do the spatial intersection at your local site. So why not just doing when the data is still in the cloud? So you can save a lot of data transportation. And also for here, we can also get like select different specific columns and also apply that filter that we also applied before. So this quality filter and also select only 3 columns. And then we can just read it in the 0.5 seconds to retrieve this point that if you're only interested with the latitude and longitude information and the 95% like relatively high information, and the quality flag actually be high quality and only intersect with the Netherlands inside and Netherlands border. You could run this low and then you get only 175 thousand of point and only 3 columns that you don't. You can you don't have to read other thing else. And so far that we show that how can we do it in a local. Everyone have like a problem or also any comment on the DocDB I wanted to share?
So it's kind of the confused. Yeah, it seems that this DB is kind of store the data that we download from the
Okay, so
what's the function?
Yeah.
Sorry.
yeah, it's okay. Yeah, it's a bit confusing. So I would say DocDB is like engine. So the engine to move stuff to okay, I gotta bring this to A to B, bring this to A to B, and the parquet is the object.
Oh, okay. So it means that now the data is still on the cloud.
The data is still here. The data is physically here, and DocDB just to interact with this physical files over here. So this from the file is to interact with this file, and DocDB is just the engine.
Okay.
Yeah.
Yeah. Thanks.
Back. Hey, I'll be back.
Oh.
Thank you. So does DocDB come with all of the kind of same geospatial functions that PostGIS would come with, like by default?
Yes, I think so. I think it's also, I didn't like really investigate a lot of the different functionality, but I assume that based on the SQL language, they could already implement most of them. I'm not sure that all of the function has been implemented, but we can develop a little bit. Yeah. Okay. So things that people like DocDB. I also like this. I also like it until I discovered that. I felt like, okay, it's so very efficient to actually access the file, because I want to also show a little bit of the demo that DocDB can also retrieve multiple files from the cloud at one common. So this is the file that we get from the data, and also it was like about 10 files that we saved as before. So using the DocDB, I can literally just read the 10 URLs at the same time as a list in the Python and do the filtering. And then we'll do in the background parallelization to interact with each file and then to filter out this and then load to your local and then kind of like arrange that in the single file. So it just this 1, 2, 3, I don't know how many lines of the code, and you can already download all the stuff. You don't have to write a for loop to actually retrieve the file by file. Also write a parallelization code to do everything in parallel and also append the data. But DocDB already deal with this all for you, and really efficient, I will say. So I spent like 36 seconds, but I filled out all of the points. You can see it's 2 million points that all intersect in the Netherlands, have high quality at the back, and also select all these 3 columns. Using DocDB, it's just few lines of code that you can already arrange with this. So I really like it. And this one, yeah. So you also were wondering that probably you haven't noticed, but I didn't mention. So basically, the GeoParquet, they arrange the geometry in the binary format, in the well-known binary, and that is one of the most efficient formats to actually store geometry. So if you wanted to export the geometry into GeoPandas format that can be read by GeoJSON and or like GeoPackage, you have to actually do some conversion. So that's that I will like to do some conversion. So the extra step that I do here is to change the geometry into known binary for this data set and read the same thing. And if you do this step, you create a new column. That name is geo_kb or WKB. And using that, you can apply the WKB loading and to extract into a geometry. And using this, you can finally get to like a GeoJSON format and download it. So when I do this, and I can, I need to run a while until it download it. So I can do this conversion into WKB and using that to convert into GeoPandas readable geometry, and then use that to save into GeoJSON if I want to do visualization on the, for example, I got it here. And I really like this feature because I really need to do most of the time visualization of the data. So if I wanted to know if my data operate correctly, I would do is to export into GeoJSON, and I open like QGIS and to see if my operation is success. So that's why also I say that GeoJSON or GeoPackage is more, it's also very important because it's really handy just to visualize things. So you see here, okay, another row is not best. And you can see that, okay, I got to see all the Jedi point for the Netherlands. And you can see this line because Jedi don't go above the 52 north. But you can still get the data from Wageningen. It's still inside the Jedi Ridge. So in this way, you can visualize your data set using, I saving 5,000 samples. Because if I save all the data set, I might have to take 10 minutes because your JSON is compiled so slow. But if you do it this way, it's actually pretty fast. And here's again, I have some comparison table to compare .db arrow and GeoPandas according to what I just showed. So interestingly, that we found out like arrow and the .db have this kind of columns selection and then predicted bootstrap. And specific for .db, you have this spatial filter, which is more efficient, more like easy way to handle geospatial data. So that's the kind of way to deal with the big amount of the geospatial data according to the data set we have right now. And that is the part of my presentation. And sorry for the time. I also prepared another tutorial, but you are so welcome to actually go for that because I'm not gonna cover right now. So it's another tutorial that I use this Jedi point to overlay with no, it's okay. The wrong okay, I'll have to replace a little bit. So sorry, this one. So I create another data set that is overlay and filter and stratify this Jedi for canopy height modeling. So this is I didn't show with this. So this is the script that I inferred using this functionality to build up the overlay and stratification for this data specific for the hackathon. So if you go to the hackathon, you will find out there is one hackathon they're using Jedi to map the canopy height for the Netherlands. It's a data set that I just present right now. So it'd be interesting to reproduce the result that you see as a point. You are welcome to run this script that you will more or less get in the similar result because I'm not sure if I would say the relevant state at the relevant state. Yeah, we're gonna changing here. So I'm gonna run your, okay. Hi, going so long. Okay, I will do it later. I need to finish the slide. I have 2 minutes. So I hope like everyone enjoyed a bit of this section. And if you have any more questions because I didn't recover everything, you can just come to me. And the last thing I wanted to also express a little bit of the formulation for like open source development about like, you know, how this actually have an impact on your real time. So this is the post like from a person called Matt Doris. Is probably well known, my open source developing guy. Is actually comparing the cost with using cloud optimized vector data VM tile to host the base map and comparing the cost for what is that 10 million requests for the tile request for the service, and to compare the cost of how can the cloud optimize vector data, the proto map is the VM tile format, how much you can save at the cost if you optimize your data into a right format and service as a service. If you go like Google, it can cost you like 3,700 euro US dollar. But if you use proto map on the right server, you only have 200, even like 12 US dollar per month if you serve the same thing at the same kind of efficiency. So this is the power of cloud optimized format in the nowadays business. And this is the main takeaway. And this is what I cover in the section. So the raster and vector, they are analyzed ready. And this cloud native format, what is cloud native formats doing? And also depends on the use case. It's also recommended to you a specific vector data. So I will come back to this slide again. So depends on what you really want to achieve. You will probably have to backward for most of the situation, overall scenario in the cloud native format. So yeah, just keep it slides in mind, and thank you for listening.